Kansas beat.
All right.
Lost to Charlotte.
Sorry to interrupt all this fascinating conversation, but good morning, everybody.
It was 48-0.
And welcome back to Calc 1. Plan for today is I have a quiz for you on Standard 13, and then we are going to continue our discussion from last class of linearization, how to use tangent lines to approximate values of functions at various points. My next office hours are going to be on Monday at 11 and at 2. The current plan is to have a Standard 14 quiz on Monday. Homework 17, which will be due on Wednesday. And also, don't forget you have a homework due tonight. So, a couple of you are astute observers and have noticed that after Standard 14, we're supposed to have another midterm. So, what I was currently thinking is midterm Monday on Standard 4. No, I'm kidding. I was thinking either next Friday or 2 Mondays from now for the next exam. And, what do you all? Any preferences on that?
Like the Friday.
All right, let's put it to a vote. All those in favor of next Friday. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15. That is a majority. Okay, so next exam will be next Friday. It will have questions on it from standards 1 through 14. As promised, every exam in this class is cumulative. Dr. Gerstel, how on earth are we supposed to do this how on earth are we supposed to do 14 standards worth of questions? You're not. The idea is that going forward, each exam, I do not expect that you will have time to complete the entire exam during class. What my recommendation is going to be, as far as heading into the exam, is going to be picking out, say, maybe like six or so standards that you're planning to test over on that exam. And even if you still need like masteries in 10 or so standards, I think the best, my recommendation is to let some of those go. So just focus on trying to do 6 or so you have plenty of time to work on each one. You still have, just like with the last exam, you can have one sheet of notes front and back, whatever you want written on it. But yeah, otherwise they'll be very similar in format to the last exam. We'll have just 1 page for each question. Do the ones you want, skip the ones that either you don't feel prepared for or you're just letting go for this exam, or skip anything, of course, that you already have 2 masters in. Any questions or comments about the exam? Alrighty, in that case, one day a student goes to his teacher and says, "The computer ate my data. I think it's trying to get me in trouble." Teacher responded, "Look, you should know better than to anthropomorphize computers. They hate it when you do that." Okay, and with that, it is quiz time. Go ahead and when you get this quiz, make sure you read it carefully. The joke is that anthropomorphize means treat it like humans, and the teacher was anthropomorphizing this computers even as students did not. Anyways, here you go. Have fun.
Thank you.
As a hint, make sure you've read the pieces of information I gave you carefully.
Exactly.
Let's see. go ahead and take a few seconds to finish up your thoughts. And pass your quizzes in, please. Pass your quizzes in, please.
Well, we either both did good or we both did bad. It's gonna get me in trouble. Keep it down. Gonna get me kicked out of school, Joe.
You guys. Alrighty.
Yeah, worst roommate I guess
Wow. You roommates?
He's actually gotten me up for the last 2 days of recording.
Alrighty, let's come back together.
I used to be the roommate.
So, good thing you got out.
No, it's kind of
So, when we left off alright, let's talk about roommates. When we left off last time, we were looking at the topic of linearization. In other words, how to find a tangent line to a function, the equation for one, at a particular point. And the example we were looking at was the square root function, f of x equals square root of x. And what I wanted to do was to find the tangent line to the square root function at x equals 4, this L of x formula, and use that tangent line to approximate what square root of 4.2 should be approximately equal to. And what we saw last time is that if we use this formula to help us find the formula to find what the tangent line is, where here, if we're finding the tangent line to the function f of x at x equals a, in this case our a would be equal to 4, we found that the tangent line has formula L of x equals f of a plus f prime of a times x, the quantity x minus a. And we found this using a point slope formula for a line. And for this particular function, at x equals 4, or at a equals 4, we got a tangent line of L of x equals 1/4 x plus 1, or y equals 1/4 x plus 1. And what we did was we said that, well, since x equals 4 and 4.2 are pretty close together, the tangent line to f of x at x equals 4.2 should be pretty close in y value to the actual function f of x at x equals 4.2. So that if we wanted to approximate the square root of 4.2 using our tangent line approximation, we said that, well, square root of 4.2 is just f of 4.2, where we plug 4.2 into our function f of x, which is the square root function. And we said that since f of 4.2 and L of 4.2 should be pretty close to each other, we could find L of 4.2 instead, which is a lot easier because you just have to take 1/4 of that number plus 1, and we got 2.05. Whereas the actual square root of 4.2 came out to 2.0494 ... It's an infinite decimal that goes on forever. And you all said that, hey, that looked like it gave us a pretty good approximation. 2.05, 2.0494, pretty close to each other. And at the end of class, what we did was we tried to use the same tangent line to approximate square root of 17, where the actual square root of 17 is a little bit over 4. It's about 4.123 ... Whereas if we plugged in 17 into our tangent line formula here, 1/4 x plus 1, turned out 1/4 of 17 plus 1 gave us 5.25. And what do you all think? is our tangent line approximation at x equals 17. Does it look like that's going to give us a pretty good approximation to the actual square root of 17? John? No? I agree. These two numbers were pretty close to each other. They were like 0.0006 apart from each other. Whereas these two numbers, they're over a full unit apart. This one's given us 4.123 and change. This one's given us something like over 1 unit bigger than that, 5.25. And so my question is, why is this approximation so bad? In other words, if we use our tangent line approximation at x equals 4 to approximate square root of 4.2 and square root of 17, why is it the case that this tangent line at x equals 4 gave us a pretty good approximation of square root of 4.2 and a pretty bad approximation of square root of 17?
Because at like the point of 4.2 or 4, the slope there is different than at 17 because this isn't a linear line. It has this gradually rounds off, thinking graphically at least. So
This
that
isn't a
tangent
linear
line is different.
I'm sorry, I stopped paying attention after you said this isn't a linear line. What's a non-linear line?
Oh. A linear graph is what I meant to say.
Yeah. So yeah, in other words, between x equals 4 and 4.2, the slope of our square root function hasn't had much time to change from how the slope behaved at x equals 4. In other words, these 2 points are so close to each other that the tangent line and the square root function haven't really had any time to diverge very much from each other. They're still pretty close. Whereas if we look at x equals 17, way out here, the square root function has had a lot of time to change course from the tangent line, way over at x equals 4. And so, all of a sudden, there's a big distance between these y values at 17 as compared to 4.2. So we can say that x equals 17 is far away from a equals 4, so the tangent line and the actual function have had a lot of time to separate, to diverge from each other. So in other words, if you're trying to use a tangent line approximation to approximate, say, something like square root of 4.2 or square root of 17, you have to take your tangent line at a nearby point. In this case, 4 and 4.2 are pretty close, so the tangent line approximation should be pretty good. Whereas 4 and 17, not so much. I'd also like to point out that the distance from here to here is even more drastic compared to the distance from here to here because this graph is very much not drawn to scale for the purposes of trying to illustrate what's going on here. But in reality, it's like if these two are that far apart, square root of L of 17 and f of 17 are probably something like this far apart. This is fun, by the way. Start pose. Any questions or comments about why L of 17 versus f of 17 is a lot bigger difference than the approximation and actual function at 4.2? So here's a question. If we wanted to approximate square root of 17, what point could we pick instead to find our tangent line at? Yeah, Elise?
Give me 16.
Why 16?
Because it's a square root. It's the 4 squared is 16. So, or no, wait.
Oh, I think
That would work. Yeah.
I was gonna say, yeah, I think you're onto something. Yeah, absolutely. 16 is a point that's much closer to 17 and it's also a, quote, pretty nice point. Meaning if we were to plug in a equals 16, finding the square root of 16 and f prime of 16 is pretty nice. Square root of 16 is 4, f prime of 16 is 1 over 2 square root of 4 is a fourth. Whereas trying to plug 17 into the square root function is not so nice. So yeah, we could say something like to approximate square root of 17 more effectively, use the tangent line at a closer point, and I agree with at least the one I would have suggested to use is at 16, which is a number that's a lot closer to 17, and it's a lot nicer to work with. Any questions or comments on that one? Okay, let's flip the page, and I want to look at another example, this time using the function f of x equals 1 over x. And what I would like to do is to approximate f of 4.9. So in other words, I would like to be able to say that f of 4.9, which is 1 over 4.9, should be about equal to what? 1 over 4.9 is not a nice number. So if we wanted to evaluate what we would get if we plugged in x equals 4.9 into the 1 over x function, what would be a value of x that's close to 4.9 that's nice to work with that we could use to find a tangent line approximation? Taylor?
Sorry, 5.
Give it a little week at first, but yeah, I think x equals 5 would be a good choice. It's close to 4.9. It's something that if we plugged into f of x, we'd know exactly what we'd get a fifth or 0.2. And so let's use the tangent line approximation at x equals 5 and see what we can find. So we're going to approximate f of 4.9 using the tangent line to f of x, the linearization at x equals 5. So graphically, if we drew this out, we would get a tangent line that looks something like this. So that L of 4.9 looks to me to be pretty close to, but maybe a little bit smaller than the actual f of 4.9. So in this case, we're going to need to use our tangent line formula. L of x equals f of a plus f prime of a times x minus a. So here's my question. What's going to be our value of a that we end up using? Where a, if you recall, is the point, is the value of x on our graph at which we're going to be taking our tangent line. Avery? Yeah. So in general, whenever you're using the linearization formula, L of x equals f of a plus f prime of a times x minus a is always going to be the close by point that is the nice point where you actually are taking the tangent line at. So we have a equals 5 in this case. We also need f of a and f prime of a in order to plug into this formula. What's our f of a going to come out to? If we were to plug a equals 5 into our original function f of x. Yeah.
1/5.
Like so. Yeah, just by definition, if f of x is 1 over x, f of a equals 5, is just going to be 1 over 5. So the last piece of information that we're going to need is what is f prime of a. So in other words, what f prime of 5 is going to be equal to. Rachel, what would be a good piece of information that you think that we might want to find first before trying to plug in and find f prime of 5?
You would want to find f prime of x.
Yeah, I think that would be a good first step, is to find general formula for f prime of x, so that we can then just plug in 5 into that formula. So if we do that, we'll get f of x, if you recall, is 1 over x, or x to the negative 1 power. What would we get if we tried to differentiate this function and find f prime of x? What?
Negative 1 over x squared.
Yeah, I think we're going to get negative x to the negative 2 if we use the power rule on that, which is the same as negative 1 divided by x squared. Since x to the negative 2 is the same as 1 over x to the positive 2, or 1 over x squared. So what would we get if we plugged in our a equals 5 into this derivative formula?
Negative 1 over 25.
We're going to get negative 1 over 5 squared, which is in fact negative 1 over 25. Neato magneto. Any questions or comments so far? So A is just the point nearby where we're taking our tangent line at. F of A is just plug that value of A, in this case 5, into the original function. F prime of A is plug in our number a equals 5 into the derivative of f of x. And now, I think we can use our tangent line approximation formula. L of x equals f of a plus f prime of a times x minus a. Look in. If we plug in the numbers that we found for f of a, f prime of a, and just plain old a, what are we going to get when we in this formula?
So L of x will equal 5 plus 1 over 5 times 5 minus, or no, my bad, 4.9 minus 8, or 5.
Yeah, it's going to be, well, let's not plug in x equals 4.9 just yet. We'll do that in a second. But yeah, we'll have x minus 5. What did you say for f of a and f prime of a?
F of a is, ooh, my bad, did I say, or negative 1 over 25. So that's f prime of a. Sorry.
Yeah, I was gonna say, I think you had it backwards the way you said it.
I'm sorry.
No worries.
And then 5. For F of A. 5, sorry.
Got there eventually. Yeah, I think for our linearization formula here, we're going to get 1/5 minus 1 over 25 times the quantity x minus 5. And this is going to give us a formula for our tangent line to f of x taken at x equals 5. And we can simplify this if we'd like. That would give us 1/5 minus 1/25 x. Negative 1/25 times negative 5, I think is going to become plus 5 over 25. It's just another copy of a fifth. So it looks like our L of x is going to come out to negative 1/25 x plus 2 over 5 when we simplify what we get. So this is just using the formula we found last time, the one that was given to us by the point slope formula for a line. We plug in our a, f of a, and f prime of a. We get this expression, which if we want, we can then simplify. So now, Logan, I think you had suggested what you wanted to do with this equation. How can we use this equation to actually approximate 1 over 4.9, or f of 4.9?
So now we can plug in 4.9 as x.
Yeah, we can plug in 4.9 for x, and then see what that comes out to. And so it's going to turn out that our f of 4.9, or 1 over 4.9 I should say, which is equal to f of 4.9, that should be approximately equal to L of 4.9, which is going to be negative 1/25 times 4.9 plus 2/5, which comes out to 0.204. I did this math. I did this calculation myself earlier. So let's see, is this a good approximation? Well, the actual 1 over 4.9 is turned out to be equal to 0.20408. Going on forever. Tyra, what do you think? Was this a pretty good approximation to the actual 1 over 4.9?
Yeah, that's pretty close.
It's very, very, very slightly under this. 0.00008 less than that. Which, if we look at the graph, I think is about what we expected, that these two answers are going to be pretty close, but that our tangent line approximation, L of 4.9, ended up being just very slightly less than the actual f of 4.9, the 1 over 4.9. Yeah, Zach?
On the quiz, will we just leave it as negative 1 over 25, 4.9 plus 2 over 5, because we're not going to be able to use a calculator on the quiz?
On the quiz, that'll come out to an expression that's easier to work with.
Oh, okay.
This is a little bit ugly, negative 21/25 times 4.9. On the quiz, it'll be nicer, and you shouldn't need a calculator to calculate out what that comes out to. Yes, when?
Are you okay with us plugging in our value for x sooner?
Ooh, so are you thinking about plugging it in maybe at this step or something?
Yeah.
That's exactly what I had in mind as well.
Okay.
So if we do that, we would get 1/5 minus 1/25 times, what, negative 0.1? And that would be a way that, well, some amount of work, but maybe a little bit easier than trying to calculate out negative 1/25 times 4.9. We'd have negative 1/25 times 0.1 instead, which is a little bit nicer. Yeah, that would certainly be good, or certainly something you could do. We didn't necessarily need to simplify our L of x. We could have just plugged it in at this step, and we'd have gotten the same answer in the end. Yeah, good question. All right. Could we have used this tangent line approximation to approximate 1 over 5.2, do you think? I heard a yes from the middle of the room. Who was the, right, yes, sir. That did not sound like you, Rachel, but I'll allow you to answer anyways.
Yes.
You think so? Why would this give us a pretty good approximation at for 1 over 5.2?
Because it would still be really close to the,
Yeah, because x equals, what value of x are we going to be looking at here? Yeah, if we were to look at x equals 5.2, the tangent line and the actual function are still going to be pretty close to each other because 5.2 is close to x equals 5. So if we write this out, we can say, if we're asking, does this L of x give a good approximation at x equal 1 over 5.2, I think I agree with Rachel and the mystery middle of the room person that yes, it would, because x equals 5.2 is still very close to x equals 5, just like how x equals 4.9 is still pretty close to x equals 5. How about if we tried to use this to approximate 1 over 9.2? There's a gives us his seal of disapproval. Why is that?
It's too far away from 5.
What's too far away from 5?
9.2.
Yeah, if we tried to go way out here to x equals 9.2, our f of x and our L of x would give us pretty different values. In fact, L of x here would probably tell us that 1 over 9.2 might come out to something negative, which is definitely not true since 1 and 9.2 are both positive numbers. So dividing one by the other should give us something positive. Anything else?
at what point does it become too far?
Oh, well, there's not really a single point. I mean, it basically comes out to what is your definition of too far? So, like, how much precision do we actually need, I would say? I would probably say any level of precision that says 1 over 9.2 is something negative is probably not very good for an approximation. Is 0.204 as compared to 0.20408 close enough? I don't know. If you're taking a Calc 1 exam, probably. If you're trying to build a bridge and you need to know like 10 correct decimal places, how correct is this so that you structure something just right so the bridge doesn't collapse, is that good enough? Probably not. It sort of depends on the scenario that you're looking at as to whether this is a good enough approximation. And that's an excellent question. I'm glad you asked that. How do you know when close enough? How do you know how close is close enough? The answer comes down to what's the scenario that you're looking at. This is by no means the most effective way at coming up with an approximation. If you go on to take Calc 2, you can actually look at how can we approximate not just using the tangent line, but say a tangent parabola, or a tangent degree 3 or 4 or 5 or degree infinity polynomial. And you can get much more accurate approximations. Those get a little bit more complicated though. So in this class, I thought, I'm going to introduce you to the idea of just using the tangent line to approximate. So for x equals 9.2, as Joseph said, I would say, is this going to give us a good approximation? No, as x equals 9.2 is pretty far from x equals. Before you all turn the page in a giant class-wide Russell paper, if we wanted to approximate 1 over 9.2, what could we do instead? Laura?
We need a point closer to 9.1 so we could use 9.
I don't know, point closer to, we want to point closer to 9.1 so we could use 9?
Yeah.
Sounds good. I would say closer to 9.2, but
Oh,
hey, I'm not judging.
2.
Yeah, so we would need if we wanted to get a better approximation of 1 over 9.2, we should probably find a nice point closer to 9.2 to work with. And I agree, in this case, I think x equals 9 would be a pretty good one. Because we know what f of 9 is going to be, it's a 9. Try using a tangent line at, for instance, x equals 9 instead. Would probably give us a better approximation of 1 over 9.2, whereas our tangent line at 5 is probably going to give us a pretty good approximation of 1 over 5.2. So is it close enough for Danielle? I don't know. Questions, comments, concerns? All right, I'm going to go ahead and skip the next page for now. The next page is very similar to the last couple problems. Just use the linearization that you're asked to find to approximate. Let's try something. Let's try something a little bit more spicy now. I want to approximate 1.01 raised to the 8th power. So is everyone okay here if we if we spend the class time to multiply out 1.01 times 1.01 times 1.01 times 1.01 times 1.01 times dot dot dot? Elizabeth and Zach are both nodding their heads. They're gonna dare me to try and multiply all that out by hand. Don't worry, I do not respond to such dares. So I don't want to multiply that all out by hand. That sounds hard. Could we do it? Yes, we had a lot of time and a lot of patience, and a crippling sadness that makes it so we don't have anything more fun to do with our lives. Okay, so here's my question. How could we use a tangent line approximation to approximate this expression instead? And this is a kind of question that you're more likely to get in the real world, and potentially on a quiz, is not, here is a function, here is a value of x to work with, find the linearization there to approximate blah. And in the last couple problems, I explicitly gave you a function f of x. And then Riley, I think you said, oh, here's a point that's close by that we could use to approximate. Here, I'm not even giving you a specific function to work with, the f of x. This time we have to come up with the f of x on our own. And if you notice, at the top of the page, I actually give you sort of a 4-step algorithm, a 4-step process for if you're not actually given a function or anything to work with, you're just being told approximate 1.01 to the 8th. What can you do to kind of come up with your own tangent line approximation to approximate that? And the first step is always going to be to find a function, f of x, and a constant, c. So the expression you want to approximate is f of c. So this is at the top of this page if you don't want to have to write this down necessarily. So here's my question. What would be a function f of x and a constant value c that if we were to plug in f of c, we were to take our constant c and plug it into our function f of x, that would give us 1.01 raised to the 8th power. Josh?
F of x just be 1 and c be like 1 to the 7th?
Like that?
Does that work?
Well, if we plug in our x equals c, which is, I think is going to be 1, because 1 to the 7th is 1, and plug that in for x in this formula here, is that going to give us 1.01 raised to the 8th power?
No.
Oh, I think you're thinking about like the next step already, which is good, but patience, Padawan. Mackenzie?
F of x would be x to the 8th power
Okay, and c?
is 1.01.
Like that? Yeah, I think that's more a better way to go for it here, because if we were to take our constant value c and replace the x and x to the 8th with that c, it would in fact give us 1.01 raised to the 8th power. Meaning for this f of x, function f of x, and this constant c, if we were to plug in f of c, we would get whatever 1.01 raised to the 8th power is equal to. Our second step is going to be, once we have our f of x and our value of x equals c that we're working with. Here's a graph, by the way, so we can kind of see what's going on. Almost looks like a parabola, actually. If we go out to here, our c is 1.01, and this is going to be our f of c. If f of x is x to the 8th. In essence, what we're looking for is finding this y-coordinate, where at our value of c equals 1.01, we want the y-coordinate of the point on our graph of f of x equals x to the 8th at that coordinate, 1.01. So step 2 is going to be find a value of a that is close to x equals c, so that f of a is relatively easy to find. And so here, what we want is a number a that is pretty close to 1.01. And we want a number that's close enough to 1.01, and so that if we were to take that number to the 8th power, we would know how to do it. Wynn, can you think of a number that's close to 1.01 that's easy to take to the 8th power? 1. Well, 1 is pretty easy to take to the, or 1, a equals 1 would definitely be close to 1.01. Close enough for you, Danielle?
I think so.
What's 1 to the 8th power?
1.
Oh, that sounds pretty easy to find. Yeah, I think that's a good choice. It's close to a equals 1 point, or c equals 1.01. It's pretty nice and easy to work with. 1.01 to the 8th is hard, but 1 to the 8th is just 1 times 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 1. That's just 1. No matter how many times you multiply 1 by itself, you get 1. So I think that's a good point to work with. And then in step 3, what we're going to do is we're going to find the linearization at x equals a. So in other words, we're going to use our L of x formula, f of a plus f prime of a times x minus a. And we're going to find what does that come out to for this specific function f of x at the value of a that when found, which was a equals 1. So when said that a equals 1, f of a is just going to be 1 to the 8th, which is also 1. Yes, Joseph?
Is it e to the 7th for f prime?
Well, so maybe we should write out over here to the side first. If f of x is x to the 8th, what's f prime of x going to be?
8x to the 7th.
Let's just use the power rule. Derivative of x to the 8th is 8x to the 7th. So if we plug in 1 for a and take 8 times 1 to the 7th, what's that going to give us?
8.
Yeah, 1 to the 7th will be 1, and 8 times 1 is 8. So I think that'll give us our information we need to use the linearization. Once we know what our a is 1, we just plug it into the original function to find f of a, and the derivative of the original function to find f prime of a. And with that in mind, let's see. Helen, what are we going to get for L of x tangent line formula?
You get 1 plus 8 times x minus 1.
Like that? I like it. We plug in 1 for a, 1 for f of a, and 8 for f prime of a into our formula, and we'll get 1 plus 8 times the quantity x minus 1. Which, if we want to, we could simplify out to 1 plus 8x minus 8, which is going to be 8x minus 7. So now, that's going to tell us if we take our tangent line at this point right here, should not be going above. I can draw straight lines. Our L of x taken at x equals 1 is going to be 8x minus 7. And then finally, our last step that we're going to be looking at, step 4 is going to be use this L of x to approximate our original f of c. So now that we know what our L of x is, we could say that L of c, in this case, which is the same as L of 1.01, that's going to give us 8 times 1.01 minus 7. And Zach, I think this would be a bit more indicative of the sort of thing that you would have to do on a quiz. Something like this, which I expect you could calculate a little easier by hand. In fact, I'll let you do the honors. What are we going to get if we multiply out 8 times 1.01?
8.08.
Yep. And when we subtract 7?
1.08.
And there's our approximation. That 1.01 to the 8th power is approximately equal to 1.08. All right, so the actual 1.01 raised to the 8th power is going to be about 1.0828, ... Danielle, what do you think? Is that close enough? Is that a good approximation?
I think so.
Think so? It's a little bit further away than our previous two. And the reason for that is that x to the 8th grows really, 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 really fast. It's like a parabola on steroids. If we graphed it, it would look something like this. And so even just going from x equals 1 to x equals 1.01, this thing grows so fast that the tangent line and that the function has time to pull away from the tangent line a little bit, but not too far away. So we get 1.08 versus 1.0828. Is that close enough? And I would say it depends on the scenario. Danielle was fine with it though, so I'm going to be fine with it. So here's the scoop. Given this, and just so you know, on the quiz on Monday, you're going to get one like this. If I ask you to approximate something using a tangent line approximation, like say, ask you to approximate 1.01 to the 8, and I don't give you a function or a value of a to work with, then you need to kind of come up with the function yourself. So first step is given an expression like this, say, what's your function? X to the 8th, I think, is a good choice of function. And a value of c, where if you were to plug that value of c into your f of x, you would get 1.01 to the 8th exactly. Once you do that, pick a value of a nice number that's close to your value of c. That is, and nice meaning your a needs to be something that's easy to plug into the function. So in this case, Wynn noticed that, hey, if our f of x is x to the 8th, and we're looking at that expression at x equals 1.01, a number that's close to 1.01 that's nice to work with would be a equals 1. And in general, you just kind of have to eyeball it and see what looks like it'll be easy to work with. Don't worry, on the quiz, I'll give you something that has a pretty nice value of a close by. So we found a equals 1. Find our linearization at x equals a at this nice point nearby, which is the f of a plus f prime of a times x minus a formula. And then, in the last step, approximate at x equals c by plugging in your c into your linearization function, which in this case meant plugging in 1.01 into 8x minus 7 to get 1.08. Wynn's sitting over there thinking right now, so Dr. Gerstle, I didn't want to find 8x minus 7. I just wanted to plug 1.01 in right here and get 1 plus 8 times 1.01 minus 1, which is 1 plus 8 times 0.01, which is 1.08. That's also perfectly fine. If you want to plug it in here versus here, that comes down to a matter of personal preference. Sometimes it's a little easier to use one than the other. In this case, I think they both are about the same level of difficulty. Questions, comments, or concerns? All right, in our last few minutes then, I have one I'd like for you all to look at, which is going to be at the end here. I want you to approximate 4 divided by 2.1 quantity cubed. Disgusting right here. So I didn't budget my time correctly, and we don't actually have enough time really for me to give you all like a good 5-10 minutes to work on this in small groups. So how about this? We'll set this one up together as a class, and then I'll let you go for the day. So if you wanted to take 4 over 2.1 quantity cubed, if we look at step 1, and by the way, you don't have to label each step as you go through. I wanted to write out all the steps for this one example, but you don't have to write out steps like that each time. Just make sure you show all your work. What would be a function f of x and a constant value c that would make it so 4 over Oops, 4 is not being cubed. My bad. Can't read my own examples. What would be a function f of x in a constant c such that 4 divided by 2.1 cubed would give us f of c? Tyra?
We do 4 over x.
And c?
2.
I think you're jumping ahead to the next step in finding our a. We want something that'll give us exactly 4 over 2.1 cubed here.
Oh.
4 over x cubed and c equals 2.1. Rachel, is that what you were going to suggest? I like it. Yeah, if we plugged in x equals 2.1 into 4 over x cubed here, we would get 4 over 2.1 cubed. So, fair out, since I think you wanted to answer this question. What would be a nice value of a that's close to 2.1 that would be not so bad to plug into our f of x function? I would say 2 is close to 2.1. And 4 over 2 cubed, that's going to be 4 over 8. That's just a half. That's not so bad to find. So I like it. I think that's a good value of a that's close to 2.1. That's a lot easier to work with in our f of x function. And so then the next step would be L of x equals f of 2 plus f prime of 2 times x minus 2. Which in the interest of time, I'll just tell you is going to come out to negative 3/4 x plus 2. I'll let you all work out the details in between. But you would just find f of 2, you find f prime of 2. These are all things we talked about how to do back in standard 5. And finally, what would be our last step in approximating 4 over 2.1 cubed? Rachel?
You would plug 2.1 into the L of x.
Yeah, we would take that L of 2.1 is negative 3/4 times 2.1 plus 2, which will eventually come out to 0.425. Sorry, that last one I had to go through a bit quickly here. But I think the most important thing to keep in mind for a problem like this is these first 2 steps. Find your f. F of c needs to be exactly the expression you want to approximate. Your a is a close point nearby that's easier to work with than c. And then make sure you find your linearization at x equals. All right, when we come back on Monday, we will have standard 14 quiz, and we will also start standard 15 and look at the first derivative test, finding maxima and minima. Good day, everybody. I'll see you all on Monday. Have a good weekend, everybody.